Tudo bem?
Tudo bem?
Sim. Ah, it's better.
Vamos lá?
Okay, so we are here with Sinai Robins. The presentation is going to be in English, so he is a professor here in IME-USP. He studied number theory and discrete geometry, or, well, discrete math in general, yeah. And here he is going to present recent results from that year, right?
From this year, yeah.
Yeah, this year, yeah. So, yeah, let's start. Oh, yeah, and the title is How do you count integer points in... Oh, God, I forgot.
Polytopes.
Yeah, on polytope. Okay, thanks.
So this is, it's a classical question, but the methods have been very, very diverse. So traditionally, this goes back to Minkowski. Minkowski geometry of numbers. However, the modern methods are so diverse that it goes, this attempts to solve this problem go through algebraic geometry, mostly these days toric varieties in algebraic geometry. In discrete geometry, we have different methods, and I've used Fourier analysis, so I'll present a little bit, not today, but tomorrow or Friday, the Fourier analytic methods, Poisson summation in particular methods. And we can even see in one dimension. I'll start very slowly today in one dimension, so we can go together and hopefully everybody will all stay together. There's a game that I played when I was this tall with my dog, and the game in English, the game is called Rodeo, and it's you jump on the back of the dog and you see how long you can stay on. And the dog will start running and going like this, and then you try to stay on as long as possible. So let's see how long you can stay on. I'll start slowly, like the dog, and you try to stay on my back, and I'll start running and running faster and faster, and then you'll see, let's see, okay? When you feel like you start falling, please ask questions. So in two dimensions, this is in RD. In two dimensions, it's kind of easy to count points, yeah, or at least it seems easy. You just look at the lattice, two-dimensional lattice, and you intersect the lattice with a polygon. It's still not really easy. So for instance, in number theory, there's something called Gauss's law of quadratic reciprocity. How many have heard of Gauss's law of quadratic reciprocity? So yeah, so it's hiding in here, in fact. If you're really able to count very well, then you can prove Gauss's law of quadratic reciprocity very easily. And that proof goes via a more subtle counting. So counting sounds easy, but gets kind of very, very deep into many things. In particular, something I was really happy to discover in January of this year is this has to do with dynamical systems. So there's a very interesting dynamical system that's easy, that's very easy to define, that I'll define and I'll draw pictures for you. Yeah, so I couldn't stay away from dynamical systems. I tried, but I couldn't. Yeah. So there's a very easy dynamical system on a flat torus. And the flat torus, at every vertex of the polygon, turns out there's a flat torus. There's a half-open parallelepiped. We'll get into this. And so there's a little flat torus here. So this is parallel to this is parallel to this. And if you identify the sides, you get a flat torus. And it turns out that the integer points inside this flat torus, they kind of start moving in a dynamical system way that's hiding. So this is a static picture, but there's a dynamic picture when these things start moving. All the points start moving in the same direction. They form closed geodesics, periodic geodesics on the flat torus. And it turns out that so now, since January of this year, now we know that these dynamical systems are hiding in there, and they're responsible for a lot of the more subtle questions about Earhart theory. So what we don't know yet, and this is only because it's new, it's of January of this year, we don't know how these dynamical systems interact. We do not know yet, we should always say yet, like ChatGPT is not conscious yet, right? So we do not know how these, and I'll get into this, into the formulas, how they interact. I'll make this very precise on Thursday and Friday. So there are many, many open problems about the number theory, but now, as of this year, it's also dynamical systems, and it's also some other things. Okay, let's start very, very slowly. So I'm the dog, and I'm going to start just walking. And so in dimension 1, let's say you're at the origin, and you just want to count, and you want to count points. You fix an integer n is some positive integer, and you want to count, and here it's very easy to count the points between 0 and n. Well, there are n plus 1 of them in dimension 1. You might say, well, I don't want to just look at it because I want to extend dimension 1 to higher dimensions like this, and tetrahedrons in 3 dimensions, and polytopes in 187 dimensions. I want to be able to do something analytically. So you might think of something like, and this is very classical number theory. You can say, let's see. So I'm going to add this from 0 to n minus 1. If you think of doing this, summing the complex exponentials, and again, this is any first-year undergraduate. Do you know? Does anybody know a nice closed form for this? Anybody know a nice closed form? How do we sum this in a very quick way? I know you know, but how do you sum this very quickly?
This is just a geometric progression.
Very good, geometric series, very good. So you might hear the idea, well, I'll just think of q to the m, and m goes, q to the k, where k goes from 0 to n minus 1, and you might think, well, you fix q to be the complex exponential, and then you say, let's just sum this, and once you write it this way, then it becomes very obvious that it's a geometric series, so it's q to the n minus 1 over q minus 1. Now, you might stop there, but let's not stop there. It's always good to go back to the basics and question basic assumptions, right? So you can discover new things. So let's not stop there. Let's think about this for a bit more. Let's break this up into 2 pieces. And look at the 2 pieces. Notice there's a singularity. There's a singularity at q equals 1. So these are rational functions. It's a sum of 2 rational functions with a singularity. Here, there's no singularity. Obviously, it's an entire function of q. If you want complex notation, it's an entire function. But this has singularities. But this is long. This is a long sum. Think n equals, for example, 2 to the 100. If capital N is 2 to the 100, you don't want to sum that many terms. Well, you can't. But here, if n is 2 to the 100, you can quickly compute. There are only 2 terms. There's no free lunch. You pay the cost. You pay, but it's not a high cost to pay. You're paying with a singularity, but you're able to sum quickly. So this is long, this is short. We want something like this in higher dimensions. We want to start with a long sum, maybe over all the points in some gigantic polytope in dimension 200 or 2000. And so far, all the known algorithms for this kind of stuff, they stop in dimension 10, 12, 13. They get very, very slow, and then even ChatGPT or any LLM cannot go beyond dimension 20 usually. So this is just what we know so far. Okay, so this is a very elementary complex number ideas, and you might think, well, in fact, you can use this. So if you push this a little bit further, you know that this is equal to. So this is equal to. It's equal to n or 0, right? N or 0. When is it equal to when is it equal to n? When m is 0, or when, more precisely, when n divides m. So when n divides m, you get n. So let me write it like this. Let's think about it again. So this is equal to 1 if we normalize by n, or 0. It's equal to 1 if n divides m and 0 else. Why is it 0 else? Well, I just erased the proof. That was the proof, right? Because q to the n equals 1, and then q minus 1 is 0, and so on. So that was the proof. So we just erased the proof conveniently, but that's okay. So this is also very, very easy, but some people call this the harmonic detector. You're detecting 1 if a certain elementary number theory fact is true. So in fact, you're detecting 1 if a certain rational number is an integer. So this should suggest counting integer points using some elementary but more interesting ideas. So for example, if you sum this thing, if you sum this gadget, just think of it as a gadget, a little black box that tells you, okay, I've detected an integer, or I have not detected an integer. And you can sum this black box over points. So that's one idea. Let's go to a slightly different direction. What I erased, so what I erased is exactly counting. Let's put it again. This was q to the n minus 1 over q minus 1. So let's now count these points. When q equals 1, you're counting points, right? When q equals 1, you're counting points. Wow. Yeah, but here, can you set q equals 1? We cannot exactly. You get 0 over 0. Thou shalt not divide by 0 is the 11th commandment. But you can, oh, I hope I don't upset anybody by saying 11th commandment. But you can take a limit as q approaches 1. And that's what we'll do in higher dimensions also. You can take a limit as q approaches 1, and you get the right answer. The n comes down, so you get the limit as q approaches 1 is n. So this is long, this is short. But it turns out that the short way, efficient way of writing things down is also very nice, because you can take limits and get the right answer. And so for today, the question is, how do we extend this simple idea to higher dimensions? Let's extend finite geometric sums to higher dimensions. So for today, how do we extend finite geometric sums to higher dimension, in fact, all dimensions? and which objects, well, as I guess you now see, the objects will be polytopes, in fact, rational polytopes. So I want to introduce a theorem here. Well, here's one little theorem. So how do we extend this theorem? To extend this theorem, let's not, there's a tendency to say, oh, I know this, right? Don't bother me with this, I know it. So let's fight that tendency and think a little bit more about this. How do we think a little bit more about this? There's some geometry hiding. So if you think a little bit more, you might think of, oh, maybe there's a infinite series over here that gives me one piece. And maybe there's an infinite series, another infinite series that I start from here that gives me another piece. So let's start thinking in terms of semigroups. In these infinite series are actually semi. Let's start thinking in terms of these infinite series and see if we can repackage, conceptualize this very simple fact into more interesting geometric objects that will extend to higher dimensions. So that's the idea. So now what is the geometric series? So we start with a finite geometric series. We want to write it as infinite geometric series, interactions between infinite geometric series. And that's what this is. In fact, this is an infinite geometric series. You recognize it as an infinite geometric series. And this is another one. So let's write it more precisely. So let's call this vertex 2, and let's call this vertex 1. At vertex 1, we have an infinite geometric series. And that's q. Well, we have q to the 0 plus q to the 1. The geometric series that encodes, by definition, it's going to encode all of these integers from 0 to infinity. But at v1 equals n, or n minus 1, we have another one. We have a geometric series that starts with q to the n and descends all the way to negative infinity. This geometric series, you know what it is. This geometric series, you also know what it is. It's q to the n over 1 minus q. Whoops, sorry. This is 1 minus q. Is this 1 minus q? Almost, not quite, right? Okay, now we have to wake up. Coffee. So this is not q here, it's q inverse, right? It's q to the negative power because you're descending to negative infinity. You're multiplying by 1 over q. So it's q inverse. It's important because now when you multiply by q over q, q to the n plus 1 over q minus 1. Look at this. So like a small miracle, this becomes, maybe I should go to n. So, well, okay, I'll stay here. So this becomes this sum here. So 1 over 1 minus q, if the negative 1 makes it a 1 over 1 minus q, and this becomes q to the n plus 1. So this is, let's write this, so let's give this a name now. Now it's time to start naming things. So this is going to be the vertex tangent cone, our first geometric object today. This is going to be the vertex tangent cone. And this is exactly what extends to higher dimensions. So let's call this sigma k vertex 1 of q. Okay. So this is equal to sigma, the tangent cone at v1 of q, plus sigma the tangent cone at v1, the sigma of the tangent cone at v2, at this vertex of q. So our elementary fact that we know from elementary school, in fact, is now has now become new to us, and now it's a sum of two vertex tangent cones. Is this okay so far? As this shows, obviously. There's only one little problem, that none of this makes sense. Why? Because this converges for, so this is okay, converges for the absolute value of q less than 1. And this converges because it's q inverse. This is okay for the absolute value of q inverse less than 1, right? So it's perfect, except that it makes absolutely no sense, because the domains of convergence are disjoint. So this becomes a famous phenomena called disjoint domains of convergence. So other than the fact that it's beautiful, it makes no sense, but that's okay. We can continue. You can kind of make sense of it. There's a few ways to make sense of it. Formal power series is one way. Fourier analysis is another way, by mollifying with Gaussians and taking limits, and that's what I've done in this 2024 book. Anyway, but there's a few ways to get over it. Let's not worry about convergence issues right now, although it's important and I like to worry about them. So let's think of how, so now it suggests that if we define this as some kind of nice generating function for points, and we define these as nice generators, it suggests that something more general might be true. And this is what Brion discovered. You might think this was discovered 100 years ago, but in fact it was 1988 using algebraic K-theory. And since his algebraic K-theory proofs, he had an elementary proof too, Michel Brion. He's very active today as well in France. Anyway, so since his 1988 proof, now we have about 10, 12 proofs of what I'm going to show you. I gave another one, 2024, using Fourier analysis, but it's very powerful, this extension of finite geometric series to higher dimensions. So let's do it carefully and slowly through an example in 2 dimensions. I decided to, instead of hit you with all the definitions of vertex tangent cones and domains of convergence and become very abstract quickly, you can ride the back of the dog slowly and see examples, and then let's see what happens. Okay, so what is a vertex tangent cone in 2 dimensions? I've decided to start with a very simple example of a triangle in 2 dimensions. And then tomorrow we'll get more abstract, but let's do an example. But you'll see from the example already that some very beautiful things are hiding in. So 1, 2, 3. 1, luckily, there's a lattice already on the board, and I'm going to take the 2, 3 triangle. I'm going to take this right triangle, and this is the new object, the new domain. And you can ask, well, how hard can a triangle be? But triangles can be pretty hard, right? There are many unsolved problems about triangles if you think of dynamical systems, right? Aperiodic orbits, billiards inside triangles, and so there are many, many unsolved problems. This is actually going to be related to that, but okay. So let's now think of the vertex tangent cones. But first, let's encode the integer points. What are the integer points? The integer points are points by definition that belong to the integer lattice. There's 1, 2, 3, 4, 5, 6, and 7. So let's define the corresponding function that encodes the integer points. So here we go, a more general definition. Let sigma p of z be e to the 2 pi I z inner product k, where k varies over the points in the polytope. So let's say can I assume everybody knows about polytopes a little bit? Piecewise linear objects. Yeah? The convex hull of finitely many points in Euclidean space, if you like. So I just gave two definitions. The latter definition was the convex Hall definition is called the vertex description. The former description, the inequality description, is called the hyperplane description. But it turns out they're equivalent via linear programming. In any case, let's assume that we know a little bit about just the definition of a polytope, and we just gave it, but okay. So in polytopes in 2 dimensions are just convex polygons. Polytopes in higher dimensions are intersections of half spaces that are compact. If you take intersections of half spaces that are not compact, those are called polyhedra, and that's what we're doing also. And if you consider, there are certain names that go back 2,000 years, right? A simplex, a tetrahedron, a icosahedron. I don't know all these names, but we want to just kind of generally study all of them at the same time. So this function encodes, it encodes the integer points inside. And you might say, well, how well does this encode? So 2 years ago, I was finally able to prove that this is a complete invariant. It encodes everything. So once you know this for every z, then you can reconstruct perfectly your convex object. If it's not convex, not quite true what I said, then I'm not sure if it's not convex. But there are certain things that will come up, like the genus of a non-convex object. It comes up in these formulas if you push them further, the Euler characteristic. If it's not convex, you can build this up as a finite simplicial complex. If you have a finite simplicial complex, then you have an Euler characteristic, you have Betti numbers, and so on. These things do come up here, but let's just stay grounded for a moment in these computations so you see what's going on. You can think of this obviously as Q1 to the K1, QD to the KD, where by definition Q sub j is e to the 2 pi I z sub j. So if z sub j is a complex number and z is a complex vector, so in general z is going to be just a complex vector. This is a combinatorial way to think of it, multinomial notation. In multinomial notation, you can just write q to the k. This is by definition multinomial notation, and then k varies over the same object, integer points in the object, and then this is the same thing as that. However, if you write it this way, it's fine to do combinatorics, and many combinatorialists do this. You can play an endless game like this with these things, find endless identities and so on, but it's not quite apparent what happens inside the exponential. The linear algebra, and as you know, linear algebra is very powerful. The linear algebra becomes much more apparent and transparent when you do this because of this inner product. The linear algebra is not so transparent here. So I'd prefer to stay on this side, but to write things quickly, I'll go back and forth quickly without further define. So this is the definition once and for all, and from now on we can just go back and forth quickly. So far so good? Okay, so you can think of it as a discretized Fourier transform. Why? Because the Fourier transform is an integral. It technically is a minus sign. If you integrate over the polytope, this is by definition the Fourier transform of a polytope. That's fine. We don't have to go in that direction, but it's very nice to do this and very powerful. And you can use, you can expand this. So everybody knows about Stokes' theorem in R to the D, right? Stokes' formula allows you to retract an integral over a manifold to the corresponding integral over the boundary. So you can use Stokes' formula for this, and I have in various papers, and then you can analyze what happens on the boundary of the polytope using all sorts of divergence type arguments about this exponential. So this works, and it's very, very nice, but let's discretize everything. So for now, let's forget about integrals. Once I gave a talk, we're going to be on YouTube, so I should be careful what I say. I gave a talk in place X with persons X, Y, Z, and somebody told me, now be careful. You're in a combinatoric seminar. Don't write integrals. People here are allergic to integrals. So, but that's not true here, I think. So yeah, I think you guys are not allergic to anything. So, but this is a discretized integral, but somehow it has, to my surprise, in January I discovered that this is much more powerful than this. Until January of this year, I thought that this was more powerful. Now I kind of changed my mind. I think this is more powerful. So I want to show you why. It'll take 3 days, but hopefully I can show you why. All right, so let's go back to this triangle and use this encoding. So this is called the integer point transform. And it encodes all the points in the polytope, in this case, this triangle. So here, sigma p of z, and I'll use this, we're in 2 dimensions, so you know, in fact, I'm going to let x be e to the 2 pi I z1, and I'm going to let y be e to the 2 pi I z2, just to make things faster in 2 dimensions. So this is, well, let's see, e to the 0, which is x to the 0, so it's going to be 1. This is e to the 1 comma 0 dot z1, z2, so I'm just going to write x. This is x squared. This is interesting. This is xy. So is this so far so good? This is y. This is y squared, y cubed, and this is xy, right? It's okay. We're encoding the integer points as exponents. So this is y squared and y cubed. So there are 7 integer exponents that are encoded here, either in this notation or in this notation. And so this is a polynomial in xy. So thinking back about dimension 1, you might say, okay, well, this was pretty cool. It was a nice polynomial, univariate polynomial in 1 variable, and that was a sum of 2 rational functions, as we discovered here. Maybe something similar works here. Maybe we can sum it as 2 rational functions in several variables now, in 2 variables. Let's see. Let's work it out. So far, so good? So as you can sort of imagine, algebraic geometers, they start getting very excited about this, because you can write this as a sum of rational functions. So let's see how you can write it as. So what is the? So I'll introduce you to the vertex tangent cones. So the vertex tangent cone at 0, 0. Let me call it V0 to be suggestive. So this is V0 here. This vertex is V0. This vertex is V1. And this vertex is V3. So I'll use this notation for the vertices. So the vertex tangent cone, now we saw what it was in dimension 1. What do you think it should be in dimension 2? Well, it's in dimension 1, you sit at the vertex and you look in that direction. So similarly here, if you sit at this vertex and you look in every direction that belongs to your object, you get this infinite cone. So this is the vertex tangent cone at the origin. However, if you sit at this vertex and you look into your object, you get a different cone, a geometric cone. So the vertex tangent cone there, at this point, 2, 0, which is the vertex V1, there you get a more interesting cone. So this is the vertex tangent cone at V1. And we have 3 vertex tangent cones. And we can write down the explicit definitions, but now you get it. So let's write down explicitly what this integer point transform is. You know what it is for the triangle. Let's write down what it is for the vertex tangent cone at 0, vertex tangent cone at V1, and the vertex tangent cone at V2, and sum them and see what happens. So far, so good? So far, no big deal. So let's see, the vertex tangent cone at V1, so at V0 first of all, well, you have to sum, I'll write it as exponential again, you have to sum over all k in the cone, intersect the two-dimensional lattice, but now luckily the cone here, at this infinite cone, it's a product space, right? Luckily it's a product space. It decomposes as R1 cross R1. This is not a product space. This doesn't decompose anymore. So this is more interesting. So if we understand this, then we should understand anything. If we understand this, then we don't understand almost anything, because it's just a product of two one-dimensional things. So this is not too enlightening. This will be much more enlightening. So let's do the easy part first. So it's going to be Q1 to the K1, Q2 to the K2, K1 equals 0 to infinity, K2 also equals 0 to infinity, because this is the way you can parameterize the integer points in that right-angled cone. So this is 1 over 1 minus Q1, 1 over 1 minus Q2. So easy, no big deal, but not very enlightening. You can write this as complex exponentials now as well, obviously. So these are rational functions in several variables now, and so let's see what it is. So the far more interesting thing is this vertex tangent cone. So at V1, what happens at V1? Well, now we have to think much harder, because we don't know how to parameterize the integer points here. And so if you're an algebraic geometer or symplectic geometer, you would say, well, let's desingularize something. But let's just think of it combinatorially. So here, there are two generators of the cone, and I'm going to call these generators the primitive integer vectors that generates it. So here, the vector -1, 0. So this is the vector. So this is the vector -1, 0, and I'm going to call this W1. And this vector here is the vector by definition. Well, it's -2, 3. So that's W2. And here comes the flat torus. There's a beautiful flat torus here. You can just think of this parallelogram. And if you think here, this is, let's see, I drew this in a way that's not maybe completely obvious, but if I want to find the integer points inside this half-open parallelogram. So it's just a half-open parallelogram from the perspective of discrete geometry, but topologically it's a flat torus, and that's going to be important later. So so there's one integer point here. There's another one here that's -1, 1. Is that right? If I oh, sorry. I'm at the point 2, 0. So I have to be careful. I'm thinking, sometimes I translate this to the origin, but at the point 2, 0, this is 1, 1, right? And it's inside this half-open parallelepiped, where now you move -W1 in this direction, and so this is, yeah. So now, now is there just one integer point inside this half-open parallelepiped, or more? The 0? This term, and 0, 2. Yeah, but okay, so I'm going to define my half-open parallelepiped to not include any of these vertices. I'm going to include this, the apex of the cone, but I'm not going to include these, just the interior ones and this one. Oh, yeah. Oh, yeah, thank you. So 0, 2, so this is, so I didn't do this correctly. So 0, 2, that's what you're saying? So 0, 2 should be, Should be here, so, oh, thank you. Okay. Oof, okay. 0, 2, okay. Good. Sorry? So the vector W1, I'm thinking of W1 as the vector that's starting here. I'm translating W1, it starts here and ends here, but the fundamental parallelepiped, so forget, so W1 is this, indeed it's this vector, but I'm thinking of starting here and then adding W1 to end up here. Is that okay? So we have exactly 3 integer points inside this half-open parallelepiped. So at this point, I should define what the half-open parallelepiped is. Traditionally, in discrete geometry, we use capital pi for this half-open parallelepiped at V1, and it's the set of all lambda 1 W1 plus lambda 2 W2, such that lambda 1 is, we want to be closed on this side and open on the other side. Okay, so that's, okay, so this is a fundamental parallelepiped that sits at the origin, obviously. Geometrically, I'm thinking of the fundamental parallelepiped of the cone as sitting at the vertex V1. So technically, if I want to define it like this is traditional, but if I define the fundamental parallelepiped sitting at the origin, this has, this is important for what's going to come later, this has a vertex at the origin. But this one doesn't, so this one is this one translated by V1. So this one here is pi sub V1 translated by V1. So I'm thinking of taking the one at the origin and moving it so that it becomes a fundamental. When I say fundamental, I'm thinking of a fundamental domain of a discrete group action, like some of you are doing, and I love doing also. But it's not exactly a group, it's a semi-group, but it tiles, right? So it does tile like a fundamental domain should tile by the group action. The group action is now translations, so it's an abelian group of translations. You translate by multiples of W1 and multiples of W2, integral multiples of W1, integral multiples of W2. So far, so good? Now, you might say, okay, let's take integer multiples of W2, integer multiples of W1, and mimic the finite geometric series, and parameterize the integer points by inside the cone by taking those multiples, and we're done. That would be, as ChatGPT often tells me, it's not quite true. It's funny. Just yesterday with Andre, ChatGPT discovered a lemma for us, and now I'm really going to put it in my paper, the ChatGPT lemma. And it's kind of funny. It's not hard, but to give it credit, it discovered it. So we should be honest. Anyway, so it's not quite true. It's not enough to take one geometric series generated by W1, W2, the points, because you're going to miss this point, and you're going to miss this point as well. But let's do it anyway. Let's take all the integer multiples of W1, W2, generate all integer multiples, get an infinite geometric series in one direction, an infinite geometric series in another direction, take the product, and you get all of these points. Which points do you get? Well, you get precisely the following points. You get this point, this point, this point, this point. You get all of these points. But you're going to miss this point, but then you can play a similar game. So you're going to have a product of two geometric series that catches the orange points, which is an integer sublattice. And so sublattices of the integer lattice are very important. Okay, never mind that now, but you get an integer sublattice. But if you start with this point, you also get translates of it. You get another integer sublattice. So this gives you one rational function, the orange ones, which is a product kind of two geometric series, infinite geometric series. This will give you another one. This will give you a third one. So we'll have really a sum of 3. So let's see how it goes. Let's see how that works. So the vertex tangent cone at V1, well, at V1, you have the vertex tangent cone is by definition e to the 2 pi I kz, the integer point transform of the cone. Kv1. So that's the definition of the integer point transform at the vertex v1 of the triangle. And now if we just think of the vertex and it translates under integer multiples of w1 and w2, it starts out, in other words, we want to parameterize the domain here. And what I just said, it's not enough to parameterize the domain by looking at integer multiples of w1, w2 plus the vertex. However, let's try to do it anyway. So v1 plus integer multiples of w1 and w2. And here m1 goes from 0 to infinity, m2 goes from 0 to infinity, and now you really have e to the 2 pi I v1 z, and now you can pull the v1 dot z outside, and the rest becomes, can I just write the geometric series argument down? Now it's a geometric series because m1 goes from 0 to infinity, m2 goes from, so now it's a geometric series, and you have 1 over 1 minus e to the 2 pi I w1 inner product z, and 1 minus e to the 2 pi I w2 inner product z. And you can write this in terms of q's, but I prefer right now to write it in terms of exponentials. I'll go back and forth, like we said. So far, so good? So that's not exactly the whole integer point transform. We're not done yet. It's one piece. That's the piece, so we have to add something. That's the piece that comes from the origin translated by the sublattice generated by w1, w2. What about the piece that comes from this other integer point? This one here. Well, this one is 1, comma 1. And as you pointed out, this is 0, comma 2. So we have to start here and do the whole game all over again. But we can. If we play this game and translate this by minus w1 and plus w2, that set is disjoint from this set. So being disjoint, we can just add it to the contribution to the infinite series. And so it's plus. So it's not quite this. It's this plus 2 more sums. One from, I'll just write in to abbreviate 1, 1. And another sum from 0, 2. So if you do this game, then you get this plus this plus this will be this. This is a monomial now. I'm thinking of this as, you can think of this as the monomial. What is v1? v1 is 1, 0. So this monomial in terms of the q's or the x's and y's becomes just x, because it's x to the 1, y to the 0. So this is just x in terms of the monomials that we wrote down. So in terms of these monomials, if you do this with 1, 1, then you get xy over the same thing. So now I'm going to write this as 1, and this w1 is negative 1, 0, so it's 1 minus x inverse, right? Because it's negative 1, 0, so it's x to the negative 1, y to the 0. And this one is 1 minus, well, w2 is minus 2, 3, so it's x to the minus 2, y cubed. Just to save, so I'm going to go back and forth like we said. And there's a third one that comes from 0, comma 2, and that's the third contribution. This is one contribution, second contribution. The third contribution comes from y squared because it's 0, comma 2. So the 0, comma 2 contribution comes from this point here. The 1, 1 contribution comes from this, and the 2, 0 contribution comes from this. And each contribution gives you one monomial times a product of 2 geometric series. Okay, so far so good? You're still on the back of the dog, right? So far you just, the integer points inside the integer cone become a sum of 3 monomials in the numerator, x plus xy plus y squared divided by this. Let's rewrite this cleanly over here. So far we have that this integer point transform of the tangent cone at v1, 2 comma 0 is equal to x plus xy plus y squared. Was it x?
X squared.
X squared, yeah. I thought, thank you, yeah, good. X squared divided by 1 minus x inverse times 1 minus x to the minus 2 y cubed. So it's this rational function in two variables. That is everything. Now we took care of all the integer points in the cone. It's a bit annoying that we have to take care of these other ones, right? But that's life. Now let's think about it for a second. So what did we have to take care of? We had to take care of every integer point inside this half-open parallelepiped. So think of it as a flat torus. The flat torus hits the lattice, and the complexity boils down to analyzing points in the flat torus now. So later, tomorrow and Friday, I want to show you dynamics now of the flat torus that came up in January for me. And it's on the web, you can see the archive. I don't understand yet the interaction between these dynamical systems at all the vertices. Each vertex we can analyze perfectly, but when you put them all, there's a weighted linear combination weighted by certain polynomials, multivariable polynomials called Barnes polynomials, which extend the classical Bernoulli polynomials, and those weighted linear combinations are now a new thing that we have to understand, and we don't understand, but that's okay. It's a whole branch of discrete geometry to try and understand this. It's called period collapse. Anyway, let's go now to the final. How much time do we have? Let's see. 3 minutes. Okay, perfect. So let's now analyze. Let's add the 3 vertex tangent cone contributions. So if we add them, what do we get? So finally, we'll add the 3 vertex cone contributions. Well, we computed the first one was 1 minus x times 1 minus y, where this is e to the 2 pi I z dot vertex and so on. The second one was x squared plus xy plus y squared over 1 minus x inverse. This came from the edge of the cone, and this came from the other edge of the same cone, minus 2 comma 3. So these are the edges of the cones. The complicated thing is the numerator, as you can see. And then the third thing, just to save us time, I just pre-computed because I knew that we would run into time constraints. The third thing, rational function, vertex tangent cone at V2, turns out to be, let's see what it is. It's y cubed plus xy. And here we have the edges of the vertex tangent cone at the other vertex of the triangle, so it goes in the other direction. So it's 1 minus y inverse, because from this you have this negative 1, 0. Sorry, 0, negative 1, so you have 0, negative 1, so x to the 0, y to the negative 1. And then here you have 2 minus 3, and that's the vector, this one, so that's the final tangent cone. And when you add these 3 rational functions with now, these are multivariable singularities, and these multivariable singularities are very interesting, right? They're no longer isolated, as you know, maybe from the last lecture, or in general from general complex variables. In several variables, the singularities are no longer isolated in several complex variables. That's what makes the subject harder. One of the reasons it's harder, and so but for some strange reason, this is equal to exactly a polynomial in x and y. And this polynomial, if you work it out and simplify, magically this polynomial is exactly, so this is kind of the miracle. And this is by definition sigma p of z. So the sum of the three tangent cone contributions is exactly the integer cone of the, so you might think, is this a coincidence that the sum of the vertex tangent cones always cancels and all of the weird multivariable singularities magically cancel and you get a polynomial? It's too good to be true to be a coincidence, and so indeed it was a theorem, 1988 by Brion. Now we have over 10 proofs, and I want to, this is the main tool I will use, but it's surprising that you don't need much more than this. You just need to kind of massage things now and be slightly creative, but massage things, and we'll start with this fact. I won't prove it because the proofs are involved. It would take a little longer to prove it, but now you have a good idea of what the Brion's discrete theorem says. It's really kind of magical how all these singularities cancel. It's a sort of inclusion-exclusion geometric principle, which is kind of, you can guess that it's hiding a geometric, but it's not just geometric inclusion, there's something else also beyond that. So far so good? Everybody's still on the back of the dog? Okay. All right, so very good. So we'll continue tomorrow with a slightly more advanced stuff, a little bit faster, but now you have a good idea of where we're going to the more advanced topics. I'll stop here, yeah.